Okay, so what we are going to talk about is time series models. I'm going to use my pen tablet a little more to be able to make some of these points clear. So, I could have given you a model which is f of, uh, so if I think of inputs as u, if I think of u as an input, okay, and y as an output. So first thing we can think of steady state models. So when you say steady state models, the most general way of writing is u comma y is equal to 0. So you think about any process that you have when there is no time history, you can eventually bring it into this form. But when we talk about dynamic models, so when you have dynamics into play, then your model takes the following form. You say dy by dt is equal to f of u comma y. And this is not enough. So not only is, so here u is the input and y was your output. If you could write it, so this is written in an implicit form. You could write it in an explicit form and say y is equal to some function of u. Okay. But here, in this particular case, in the dynamics case, you have not only your input u that is affecting the time trajectory of y, but what you have is also an initial condition that y at t is equal to 0 is some initial condition like y0. So here, assuming that this is a map, so for every u, you have an f that gives you a y. Okay. But here you have t, the time, that is also playing a role. And so it could happen that for a given value of u, okay, you have not just a y which is a fixed value y of t, because it keeps on evolving with time. And so we want to be able to study data-driven models for such kind of systems, for such dynamic systems. So I thought I'll just build up from uh, where we left off in random variables. So if you recall, we had said that you had a sample space, okay, and I called it omega, and we had talked about, so you had events in this omega 1, or you had elementary outcomes omega 2, and so on. And a random variable was a mapping where we had said that we map it onto the real line. So for example, omega 1 could be point like x of omega 1, and this could be x of omega 2. Example being you toss a dice or you toss a coin, and you have in heads, you say my on the real line I have the number 0, and if you have a tails, you say on the real line I have a number 1. So it was mapping from the sample space to the real line. Now that was a random variable. Okay, what we will do today is a random process. In a random process, we will say that this maps to the function space. Okay, so this is a space of functions, and we will say that omega 1, for example, maps to x1 of t. Okay, omega 2 maps to x2 of t. So for, while t need not always have the concept of time, we can think of t as time, because we're talking of dynamic systems. So we have a sample space, we have an outcome, but the outcome is no longer giving you a number like 0 and 1. But if you toss a coin, you have a function x1 of t. Let us say that is sine of t. Okay. If you get a tails, you say I get a function cos of t. This is a random process. And that is the distinction between a random variable and a random process. So we will still continue thinking in terms of a probability triplet, the the, uh, the probability space, the sample space, and the random variable mapping. But here we will think in terms of a random process. So why do we do this? We do this because we want to be able to think of that dynamic evolution of that trajectory. So we want to be able to assert, or we want to be able to describe the uncertainty in that trajectory, not just in that variable. Now, this leap is not really that great. And if I were to just show you, uh, for example, this is x1 of t, and this is x2 of t. Okay, so this is time that I have drawn on the x-axis. And let me draw here first. Let's say uh, this is 0, and so cos of 0 is 1. So you have something like this. Okay, and sine of 0 is this. All right, that is x2 of t. Now, if I fix the time t, so let's say t is equal to t1, and I'm going to fix it at this value. Okay, so t1. Then you will see that that function has only one number over here and one corresponding, that is this value and this value. Okay, then at t is equal to t1, you can see that it has just become a number. It's gone back to being a random variable. So you have a random process x of t, but if I fix t is equal to t1, you have got two realizations of that random variable x of t1. Okay. Similarly, you can have another variable x of t2. And now you'll say that time is continuous, and so you get a continuous function. So from a random process, you can always go back to a random variable by fixing the time t, and now no longer having a function, but what you have instead is the realization at that fixed time t. Okay. So that is a random process. So essentially a random process is a mapping from the sample space to the function space. However, if you fix the value of time t, then what you get is indeed a random variable. Now, you'll remember that when we did random variables, we had also looked at moments. So because of the fact that you have a new, this notion that you have a time trajectory, and you have, if I were just to draw this as one, so here one realization is one function. Okay. So I would be interested in knowing that I have two random variables, x at t1 and x at t2. Okay. So, we had barely reached bivariate random variables when I covered it in the first class. But you can, if you now look at this x of t1 and x of t2, you can think of it as two random variables, okay, at t1 and at t2. And so you can ask yourself that how does t1 change with t2? That is known as an autocorrelation. So when I say expected value of x of t1 into x of t2 is known as an autocorrelation and is a very important part of describing a random process. But note that we're still using the notion of a random variable, but we are talking about T1 and T2 as two different time points. This is an autocorrelation. So it is a correlation because, if this correlation is positive, then it tells me generally when x of T1 increases, x at T2 also increases. So a common example being, let us say you were measuring the temperature in the room right now, and let's say T1 was 5:15 and T2 was 5:30 p.m. And what can you say about the correlation between the temperature at 5:15 and 5:30? You'll say that if it got warmer at 5:15, it'll get warmer. It'll be probably be warm at 5:30, and so you'll say that the autocorrelation, it is they are positively correlated. Okay, so autocorrelation gives you a sense of how these two random variables vary with each other. Now, for any realistic process, you will agree that because there is memory in the system, okay, just like the temperature example that I gave, that when T1 minus T2, okay, when T1 and T2 are very close to each other, then the correlation is strong. And when T1 and T2 go more and more apart, the correlation probably becomes weak. Okay, probably it may not always be the case. So for seasonal processes like temperature, it will not become weak. You know that there will be some correlation between even as the time goes away because they're periodic processes. But on the whole, let us say that if I am looking at the temperature of a city, and I go to a temperature of the next city, okay, that correlation will be strong. But if I go further and further away, it might be raining somewhere, and it might be very sunny somewhere, and it might be very cold in just a nearby place. So the correlation breaks. It turns out, and again, without trying to go into too much detail, it turns out that I can now talk about a joint density. So I can talk about this. Okay. So you are now comfortable with densities, and uh, so you could have a joint density, and if the variable is such that it turns out that what is T1 and T2 is not important, but what is important is how much far are T1 and T2 away from each other. Okay. If that is the case, I will write this as T, and the next variable I will write as T plus tau. Okay. So you see that I have got rid of what is T1 and T2. Such processes, no, if this any T1 and T2, if it just depends on the distance between T1 and T2 and not the value of T1 and T2 itself, then these are known as stationary processes. Okay. As an engineer, no, I understand stationary process as time invariant process. So if you give me an equation of a heat exchanger, okay, and you tell me that you have there are no time varying parameters, so it doesn't matter if I'm modeling that heat exchanger today or if I'm modeling it 4 months later. I have the same model. Okay, then I have the same model parameters. They do not depend on the actual value of time, whether it is today or 4 months later. Then it is similar to being stationary. Okay. So when is it not stationary? If I have fouling in my heat exchanger, there are some things that are taking place in my heat exchanger which invalidate the relationship, um, you know, um, now versus 4 months later. So it will actually depend on when did you do that modeling? What was T1 and T2? In that case, you will say, oh, the process is not stationary. Okay, and we will, in engineering, we'll call it, for dynamic systems, you will say, oh, it is linear time varying system, or not linear, but it's a time varying system. So you can draw that analogy from there and think in terms of time invariant systems as stationary systems. Okay, so I have discussed with you a random process and tried to motivate how it comes. You can think of it as a collection of random variables, which also brings the notion of autocorrelation and the fact that you have a stationary process. So in a stationary process, it turns out that this expected value that I have is x of t into x of t minus or plus tau. Now it doesn't matter whether I put in minus or plus tau, and this is known as, almost universally, you will always find this r. they use this term for autocorrelation. And here I would have written this originally when I was not sure as T1. Okay, so this becomes Rx of T comma T plus tau. But since it's only a function of how far away you are, so it's become Rx of tau. Okay, so what we will do in today's class, this has a strong bearing in our ability to understand autocorrelations. So I can just tell you that physically it just tells you how is the variable value now correlated with the variable value tau seconds before or tau seconds later. Okay, so if it is a slow process, it has a lot of memory, then you will say that. So let me give you an example. So let's say I have a process whose one realization is okay. I have another process whose realization looks like this. Okay, which I'm just. You will say that in this process, the first one that I had drawn, what is the value at t over here is very strongly. It will influence what is the value tau seconds later or tau time samples later. Whereas over here, you see that, whether the value is high here, it could be very quickly, it will become low. So you say this is not not strongly correlated, whereas this one is strongly correlated. So that is the, oops, sorry about that, strongly correlated. Okay, which means that for long tau periods, the values keep having an influence. So we always talk in terms of a time constant. We say, oh, the time constant is large. And you say sometimes the time constant is small. That means the influence of the initial condition on the subsequent values essentially wears off quickly. Okay, so please keep this definition in mind. So, just because you have autocorrelation, if I had two variables, x and y, okay, I could also find out expected value of x of t into y of t plus tau. And this is known as the cross correlation. Okay, so this is an example of a cross correlation. I hope you can see that. So here x is one time series and y is another time series. Okay, let me uh, into dynamic models. So without getting bogged down too much, we'll just see where do these models come from. So for example, you have a process shown over here and you have an input u, okay, time instant. So I will talk briefly as to why we have, all data is eventually stored in a digital form. And so these dynamic systems don't model as much a differential equation, but they try to model a difference equation. So you can write, for example, you had dy by dt is equal to f of x comma y, okay, where each variable has this implicit argument of t in it. But we will not model these ordinary differential equations. What we will try to model in today's class is the difference form. So for example, if you were to use explicit Euler or if you were to use Rangakutta, where you would be able to write this entirely in form of, certain discrete values of y and x, then what we will try to write is you have y of k, okay, where k is the sample, is some function of y of k minus 1, comma u of k minus 1, comma y of k minus 2, comma u of k minus 2. And I don't know how far to go, though now we have some clarity that it depends on the memory or it depends on that autocorrelation. It depends on that cross correlation. How far in the back should we go? Okay, that what kind of past inputs are going to affect my current input y of k. So, given a process, I have an input that I inject into the system, and this is an example of that input, and what you get is the process which is reacting. And this process, of course, is a continuous time process. It is not at k. This is indeed supposed to be at y of t. But this has been plotted on a computer, and you know that this y is a series for you. It might be at 0.01 seconds, or it might be at 0.1 seconds, or it could be at 1 second. So eventually it depends, how many points do I collect? So eventually I do not collect y of t. What I collect is y of k, the discrete time. So it is, I have k, I have k plus 1, I have k plus 2, and so on. And there is some time interval which you can think of as your sample time ts. At every ts time units, I collect my next sample. Okay, so the whole idea about system, so this is known as system identification. So these time series models which we are going to talk about today, finding this, we use regression, but this has got, because it has its own name. It's called a system identification. Okay, so this system identification is essentially using regression, where you use y, okay, and using u and y, you obtain a model, and the model will be of this type, which I have just written on the top. It's just like when you did regression, you have been looking at different types of models, and the same thing is true. What I'm going to talk about after a few slides are what are these different options of models that we have, and why are there so many different types. Now, okay, let me continue. So essentially, the system identification is taking the input u, taking the output y, and finding out those model parameters. So just connect this to regression. So if I had y is equal to a1 x1 plus a2 x2, okay, then you had taken y and you had taken the inputs x1 and x2. Instead of that, I have u1 and u2. Okay, and what would be my parameters? My parameter, which I'm calling as theta, would be a1 and a2. Okay, and of course, in regression, you will remember that there is always this notion of noise that creeps in. So y is not merely the addition of a1 x1 plus a2 x2, but there is this independent noise which is always sitting in over there. Okay, so see, if there was no noise, I don't think regression and statistics would be that big a deal, because it would just be algebra. Then there would be no notion of trying to explain that uncertainty. The uncertainty really comes because of the noise. And as you must have realized that if you were to repeat this experiment and generate a new set of data, same input, identical input, if you were to run this experiment again, you would get a slightly different series. So why it is slightly different? Precisely because of this epsilon. Okay, not a random is not a random variable, but it's a random process. It's a noise process which is getting connected to my random uh, uh, to my true output. There is a noise process to which it is getting connected. Okay, so let's so now um, why we want these dynamic models. So very often dynamic models are used in an operating sense where there is operation involved. So for example, if you want to do soft sensing, there is no process that is rock steady. Processes are always going up and down, and so you have to be able to model it using a dynamic system. So that becomes extremely important that you model it as a dynamic system. So of course, in online, in control, in optimization, and a host of other, monitoring, fault diagnosis, we use such kind of models. Now, let me give you some examples. So one thing should be very clear, that whatever we do today is all going to be in form of dynamic systems. There will be no steady state system that we are going to talk about. So let's look at this four tank process, which is a very popular dynamic system, which is used very heavily in, for example, in process control, or in teaching uh, dynamics and transients. So what you see in this process is, and I'll just take, this slide has, this talk has many examples, but I'll just take one or two examples to give you an idea about where these dynamic systems are coming from. I will also use this very same example in at 7 o'clock in order to do the hands-on session. Okay, so let me go through this example. So this is a tank, and this tank has water in it. Okay, and this is a sump, so I'll call this a sump, water sump. And there are four tanks as shown over here: tank 1, tank 2, tank 3, and tank 4. So you have a pump. This is a variable speed pump, V1 or pump 1, which you've given a voltage V1. This is pump 2, to which you have given a voltage V2. Now you can see this strange arrangement. The water flows in from pump 1, and uh, it comes to this valve. This is a splitter valve. Okay, so it comes in from here, and then water goes here in this direction, and the water goes to tank 4. So you can see that water enters here and water enters over here, diagonally opposite. And so what will happen with water when it enters here? There is an orifice and water finds its way down. From tank 4, the water finds its way down to tank 2. In case of pump 2, you've given a certain voltage to the pump, and based on the setting of the splitter valve over here, you will have certain amount of water going down into tank 2 and the remaining water going into tank 3. The water from tank 2 will come down to the sump, whereas water from tank 3 will drain out into tank 1. So this is an example. It's an extremely simple example. So if you can see that, you can write down first principles model for all the four tanks, and that gives you this set of equations. Even for this very simple example, you realize that you have non-linear, because any real process is can be modeled as a linear process, but everything is inherently non-linear. Okay, so in fact, if you use these equations and you have tanks which have very little level in them, you will find that the square root nonlinearity can be quite steep, because if you plot the square root nonlinearity, you will see it looks like this. Okay, so it rises up with infinite slope, and then the slope becomes finite. Okay, so when you have, this is h, this is square root of h. So you see that when h is very small, then I have, excuse me. So once h is very small, you can see that you have, this is infinite. This is infinite slope. Okay, so it is what you will say is, is not Lipschitz continuous. So you can see that even with a square root nonlinearity, and depending on the value of h, it could be a very nice linear-like system, or it could be a highly non. Okay, so this is the challenge, that if you were trying to model this using first principles model, you would have to find out all these constants. Okay, you would have to actually do a lot of experiments, and still do experiments and find out a lot of these constants. Okay, so where does system identification come in? system identification says that we will not do a first principles model. What we will do instead is collect data. So in this case, let us say I have H1, model of H1 as a function of H1 of K. So if K, so this is K minus 1, H1 of K minus 2, and so on. V1 of K minus 1, and so on. V2 of K minus 1, and so on. This is a system identification or a time series to be able to find. So you see, the promise is that first principle system, can I find the time series model of that system directly from data? And where is its utility? Its utility is that it should be able to give you accurate predictions. The predictions should be accurate so that you could go back to these applications. Okay. So this is what, nowadays when people talk about surrogate models or proxy models or digital twins, this is where these are the types of models that you can use. Another utility of time series models is that here you need an ODE solver, or even if you're a difference equation, you need some algebraic solver in order to solve them. Okay, time series models, you can evaluate the output of the system very quickly. So let us say you were trying to do some kind of a uh, system where you needed to have your outputs very quickly. Okay, and let's say you have used this system in an optimizer. Okay, then you want some some way of getting those outputs very quickly. If in that optimizer you had put these ODEs, then solving each time the optimizer calls the function and you're solving an ODE, it would be very expensive. So that is another side advantage of time series models. Okay, so there are many examples which I have. I'll just probably look at it from a very top level. So for example, you have this normal CSTR and you have a reaction A going to B. You write down the material balance, you write down the energy balance. In the energy balance, of course, you have heat transfer to the jacket, and so you need to be able to model that too. So now, if you were a person who would write down the first principles models, though remember that when you say first principles models, these are not completely first principles, because first principles would mean that they're completely ab initio. So note that, for example, when I am trying to and find out what is the connection, or what is my model for heat transfer jacket, you will see that I still have these parameters. Okay, these parameters might be mechanistic and you might have some kind of a mechanistic understanding of these parameters. However, they are still parameters that need to be identified. Okay, so given that we have these kind of parameters to be identified even in first principles models, why not just use conversion at the end of that reactor? So let's say this is the bed length, which is L. Now you may be interested in only what is the concentration of the unreacted reactant at the end of that reactor. Okay. So again, you can use a time series model to be able to determine that. What is important, of course, is that you have measurements. So without measurements, you cannot build time series models. So you need to have Y and U. Okay. Okay. Now I've already in some sense, motivated that why you need discrete time models. So discrete, as I told you, is in any computer control application, your discrete time models are always the natural way of 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 modeling. Okay, because it is um, so. Given here is an example where you are remember the output of a process is a continuous variable, and y of k. So I'm thinking of t here as a continuous time and k as a index. Okay. Though in system identification, we very often use y of t even over here because we don't work with continuous time models, at least in any dominant sense. And then if you have y of k, you generate a control output which has to be injected into the plant, and that is u of k. So what is the difference between y of t? Y of t was this signal. And what is y of k? Y of k is that this signal has got sampled. So this is y of 1. After a sample time, I get y of 2. So it's only this value and then this value. I've ignored everything that happened in the intersample. Okay. So what I have really is not a continuous plot, but I just have the stems. I have a stem plot. Let me try to show. Oops. Here. So this is y of k. It's just a stem plot. We have no information what happens intersample. What you get u of k is again a stem plot. So you have this value, then you have this value. And so we have this digital to analog converter where we want, because you can't be giving these kind of pulses to a process. This means that always open, then close, then we don't know what happened in between, then open, a pulse and close. So that is no good. So what we do is use a zero order hold. So we say, okay, we will just go from here to here in this way. And so what you get is a a staircase kind of an input which goes over here. So what goes inside is again a staircase kind of a input. And what you get out over here is a continuous input. So when we say we are modeling between u of k here and y of k here, which means that all these have got subsumed in my model. So all of this is part of my model. It's not just the process. The process was here. What has got subsumed is also the time. What has got subsumed is any other kind of signal conditioning that might be happening over here. Okay, so the model is really between you and let us say q to the power of n, and if I give
Excuse me, sir. We are not able to hear you.
yeah, yeah, Om Prakash, could you say
Yes,
something?
sir. Sir, we were not able to hear you like before.
Oh, yeah. Has my voice? I've changed my position because I realized I was not charging. Is it better now?
It's okay. Now it's okay, but when we were explaining that now the model is between U and Y, after
Uh-huh.
that it got stopped.
Okay. So, is it better now?
Now it's okay, sir.
Okay. So, yeah. So in this case, now I was trying to, when you use UK and YK, we always think that, oh, it is between the process. Oops. We in the process u of t here and y of t here. What we forget is that there is a lot of signal conditioning, and really it is all that gets caught up over here. So when we model u of k versus y of k, we have all the signal conditioning elements as part of that model that I have. Okay, so in this case, I had started shift operator. Shift operator, I was trying to introduce this notion of Q. Okay, so because the time moves forward, apply Q. You can think of Q as the forward shift operator. And so by analogy, so this is so Q to the power of n. So it got shifted forward n samples into the future. On the other hand, if by analogy, if I put Q inverse, you will see that it becomes a backward shift. And I'm going to use the same algebra. So you have y of t over here. You have q to the power of minus 1. And what you get is one sample at the back. So it is known as the backward shift operator. Okay, that's all. So if I now write down an equation like y of t is equal to 2 times y of t minus 1 plus 3 times u of t minus 1, you can very easily make use of this shift operator. And you say, okay, y of t, I can write this as 2 times q inverse y of t plus 3 times q inverse u of t. You'll see t is common. So I could write this as y of t into 1 minus 2q inverse is equal to 3q inverse u of t. This is q inverse. And then this will allow me to write in this what we call as a transfer function form. Okay. So I'm just talking in more generic system. So a transfer function is basically input divided by output. Y of t divided by output. And you'll see it looks like this now for this 3q inverse over 1 minus 2q inverse. That is a time series model, not in its entirety, but it comes, the major elements of a time series models are there. So you remember now we talked about y of k, u of k. So you should pardon my habit of using t instead of k. Okay. So while in control literature we very often use k, in system identification literature we almost always use t. Okay. So people in signal processing literature very often use n or k, but in system identification t is an index. It is not that time. Okay. And you will see when we use the toolbox that they always use t in the system identification literature. So this that I have written over here now is an example of a time series model. It is telling you how y of t is changing with u of t. And if you would like to see the more obvious way of looking at it, it was this: y of t is equal to 2 y of t minus 1 plus 3u t of minus 3u t minus 1, 3u evaluated at t minus 1. So this q plays a very important role in describing these models without, but it really does not concern me, because eventually I think in terms of the difference form. So I can always go back from that q inverse and all that and just write it back in a difference form, which as an engineer is more intuitive. Okay. So given for example is, this is a transfer function. Okay. And this transfer function, I will, there are two elements over here. So I would write this as y of t, okay, is equal to gp1 u1 of t plus gp1 u2 of t. There are two inputs. That's why there are two elements. See what one input, one output. Very simple. Okay. But now if I had 3u1 for u2, you would see that you would not be able to write an input output over output. You would write it as y of t is equal to one element g1 times u1 plus another element g2 times, and that is what you see over here as I have tried to explain it over here. So again, there is no difference. You can always convert from the forward shift q operator to the backward shift q inverse operator. Both are equivalent. Okay. So in that sense, there is no major. So, okay, we have looked at what are random processes. We have looked at what are, I've talked about autocorrelation and why the fact that when you have a process rather than a variable. So in a variable, we talk about correlation. We had the correlation coefficient. Here we talk about autocorrelation. Why we talk about autocorrelation? Because we're talking of the same variable x, but evaluated at t1 and evaluated at t2. And here also we can correlation. We can talk about autocovariance, cross covariance, if you were to subtract out the means. Okay. So this allows us to obtain these black box models. Okay. And is true is that you get no insights into the internal working of the system. It is just a correlational connection between the input and the output, with no insights into the internal working of the system. Now, if I were a scientist, I would be very, very unhappy with this kind of a thing, because I would say my whole purpose is to understand what is the mechanism underlying in a particular phenomenon. But that is why there was an earlier slide which I had skipped very, very quickly, where I had from Leung, who said, so Leung is one of the persons who made system identification very popular, along with his colleagues like Soderstrom and others. So he says that the real life system is an object of a different kind than our mathematical models. So if you were a biochemical engineer who was trying to understand some protein uh, binding, and you wanted to understand how a protein folds and then conforms to the second protein, and that causes and that insight, but that insight you don't get through these kind of mathematical models. So in a sense, these time series kind of models are impenetrable. Okay. But they only connect input and output. So what is happening, how that protein is folding, and what are those internal workings, we don't know. We only know that yes, that a certain protein A and protein B, then you find that you can predict that what concentration of bound protein would be there, AB. Okay. So we can look through this window and compare certain aspects of the physical system, but we can never establish any exact connection between them. So, and this is the key thing, that as an engineer, our acceptance of models is guided by its utility or usefulness, okay, rather than truth. So As an engineer, I will say, oh, if I can this data and I can by end of 2 hours, I can give you a time series model. Then, by another 1 week, you can start some production somewhere. I don't know. Okay. But that is the guiding principle. It is about the utility rather than knowing any internal working that I might be able to uncover. Let me try to quickly go to the types of models. So I'm going to skip this. Let me what is is um, is linear systems. Okay, and for those of you who have heard of recurrent neural networks or this LSTM neural network, that is a non-neural construct or a non-linear construct for the same time series data. Okay, which have become extremely popular, but their basis continues to be the same. Okay, so why is it that this whole area, indeed, not only of time series, but indeed for statistical learning or regression exists? And the only reason why this exists as such a big area is because of the presence of noise. Okay, so like if you have a CSTR and you give an input concentration, then you will see that if I were to look at this blue curve, then it is the measured temperature without noise. But that is not what you get. So you remember when I wrote that linear regression, I wrote A1 x1 plus A2 x2 plus. So that was A1 x1 plus A2 x2. But what you have is epsilon. Okay, this is your output Y. And what you are asking me to do is you are asking me to solve a very tough problem of finding out what is A1 and A2 when you are not able to tell me what is epsilon. If you had told me exactly what was noise, I would have subtracted it out and I would have given you A1 and A2, deterministically. But the fact is, so there is not only so while you are able to give me x1 and x2 and y, what what I cannot back out is this noise, and that is the reason why we have all these different types of models, how to handle noise. In regression, we have so many different approaches. The whole reason is to figure out how to handle this uncertainty of noise. Okay. So you will see that these different models that I'll talk to you about now are different because of the different ways of handling noise. That's about it. Okay. So if you knew exactly what, compare it with the figure that I had tried to draw earlier when I was talking to you about correlation, and you will realize that this noise is not this type which I told you is highly correlated kind of a signal. This is very, very uncorrelated system. Okay. In knowing this, you have no clue where will be the next element. Will it be here, or whether it will be way up here, or next one would fall down over here. You had no way of telling me that given y or e, if you want to call that noise, e of k, then what is e of k plus 1? You have no idea. And so you say it's an uncorrelated signal. No, it's completely uncorrelated. And typically, not always, but very often, this is one way of modeling noise. Because I don't know what is noise, but I can model it as an uncorrelated signal. So in your linear regression class, you have already encountered this, where you thought of noise as an uncorrelated signal. Okay. You may say that that does not fit with reality, in which case you will have to remodel noise, which will lead to another type of model. Okay. And the same thing is true with these inputs. So let me, talk to you about the different types of models. And my treatment is not going to be satisfactory at all. But you can just take away that what are these different types of models and how do they come from, or where do they come from? So what we have seen so far is that you have A of y. So you have, um, you know, so A, B, F, C, D are all polynomials. Let me give you an example. So when I say A, okay, I mean 1 plus A1 Q inverse. And what is the order of that polynomial? I don't know. That is part of finding out. That is part of the system identification. And I will write it using the backward shift operator. Okay. In the same way, we will say B is also, and I'll start with B1Q inverse. I will not write 1. Why? Because U at T cannot affect Y at T, because it's not like an elastic system. No, you put a force and there is sudden displacement. This is a dynamic system. You put a force now at time T, its effect will be felt after time T. Maybe at T plus, where T plus is slight lapse of time beyond T, but only after some time. And so this one does not have 1, because remember, if I had said y of t is equal to b0 u of t, this is like that elastic system. This never happens in most capacitive systems. What you will have is that only at u at time t minus 1 can affect my output at y of t. And so I will always write this starting with from b1. Okay, and we will always follow this. Okay, C over here is, it will start with 1, and you can try to reason out why. 1 or A naught. So you could always say that this should have been A naught, okay, or this should have been C naught. But that, is a simple scaling. And so I have C NC Q to the power of minus NC, and so on. Okay, so this is like the most general form of the model that you can have. So AY is equal to B by F times U plus C by D times E, where E is that noise, which I told you is unknown. This is put into the system by me. Okay, so this is my known variable. This is noise, which is unknown. I don't have a value for it, though it enters my equation. Okay. So, now let me just see some examples of this. Skip this. So let's look at some very simple examples. And now I'll need to figure out what is the time. Om Prakash, do you know the time?
Yes, sir. 6:09.
Okay. So, so what these we had written were examples of the different types of time series models, which I here, and there are many, many more. I mean, this is not a complete list. And it turns out that for different choices, as I told you, that there are different types of time series models. Somebody will say I'm using an ARX model. Somebody will say I'm using an FIR model, or an output error model. It is a different treatment of this E of T. Okay, in all other, so you always will have a numerator and denominator for the U, but it just treats E of T differently. So let me go through some examples. Okay. And how do you find out these values? You find it out using regression. So regression is still the underlying workhorse. Okay, so let me come to OE models. So I'll write that down. So I had written AY is equal to B by times U plus C by D times E, where A, B, C, D, F were all polynomials in the shift operator Q. Now, there are two broad ways of trying to model these models. There are two broad family of models. One is known as the output error models, and the other is equation error models. Okay, and you'll see that these two come up just from your viewpoint. Okay, see, let me for a minute, write this simply. Let me write this as A. Let me take it as, or let there be A. Let me take F uh, is equal to 1, or the identity polynomial. Okay, and let me also take D as 1. Okay, so I can write this down as A y is equal to bu plus ce, right? So I can write this in two different forms, which give rise to the two forms of, or two families of models. I can write this as ce is equal to ay minus bu. Okay, so I'm saying that, because my real model that I'm always interested in is just this: ay is equal to bu, or y is equal to b by a times u. This is my, that I'm interested in. What is the output y of k, input u of k, and what is their relationship? Okay, so this is the model that I'm really interested in. So when I write down this as the difference, but now I'm not writing it like this. I'm writing it as ay is equal to bu. And then I see that the difference between ay minus bu must be because of noise. Okay. And I say that I'm going to model that noise in a particular way. This is known. So this is the error in the equation. Okay. So these models, which come from where you write it in this particular way, are known as equation error models, EEM. Okay, so this is one family of models. The second family of models says, no, I am going to consider my error not to be ay minus bu, but I'm going to consider my error to be y minus b by a times u. Okay, or y is equal to b by a times u. So see, the same equation, you could have either written it as ay is equal to bu, and then say, okay, what is the error between ay minus bu, and then model that as the error meaning the uncertainty, meaning the noise, okay, versus you write it as y is equal to b by a times u. And so what is this difference between y minus b by a times u, and how do I model this error? I'll just write it as epsilon. So here we think of the error in the output. See, this y is the output. So these are known as output error models, OE models. Okay, same thing, just how you model the noise leads to either an equation error models, which is also part of this slide, and it is also can lead to output error models, but they have, profound differences in terms of their properties and so on. So if you, for example, always had some recent measurements and you wanted to make short-term predictions, it turns out that equation error models work better. If you were thinking in terms of a simulator where you only had the some initial conditions and you wanted to do long range predictions, then probably an output error model works better. Okay. So shown here is an example of that output error model. So I will also come to what are these notations, because these are going to be important when we look at the toolbox. Okay. All right. Um, Now, as I said, no, that once if you write this as y minus or y is equal to b by a times u plus e. Okay, this is my output error model. Remember, y minus b by a times u is equal to e. So this is an output error model. So you can find out you can find out these coefficients of these polynomials. So what is time series modeling, or what is system identification? Is finding out b naught. So there is no b naught. I discussed that with you. B1 to bnb, finding out a1 to ana. Finding out these coefficients means your model is done, because now you can plug these back over here and you can use this model for, for prediction. So you will say, oh, how can you use this for prediction? There's E. So, that is not a problem. I can take an expectation on both sides. So I'll use the expectation operator. Okay. And I will see that this E, is very often is having this property. This E, which I have written here, has a property that it is mean zero. The expected value of E is zero, and its variance, which is E square, is some sigma square E, let me write. So if I take the expectation on all sides, then what is the expected value of E? Zero. So what is the expected value of Y? Is simply B by A times U, which is a deterministic quantity. And so it's just this. So what is the predictor? Predictor is this. I will call this as Y hat, my predictor. Okay. So it's not a problem, because I'm not going to use this model for prediction. I'll be taking the mean by taking the expectations, or the conditional mean more precisely, and use that for making my future predictions. So, for example, if I look at the autocorrelation RE of tau, it looks like this for an output error model. Okay. Okay, let me skip this. So again, I've mixed and matched, because I did not know how best to cover stuff in an hour and a half. So I've mixed and matched. I have already introduced you to the noise. So the noise being this. So y is equal to gu is what you are interested in. So what is g? G is some b by f or b by a, one of those. Okay, and whatever is not explained or cannot be explained by you is in this is a catch-all term. Everything that I cannot explain using you, I'm going to put it over there. It turns out that you have to be able to model V properly. For example, if this is not zero mean, then you are in trouble. Okay, because remember, we are always thinking we are going to model this V using some E, some operation on E, and the E was zero mean, and the variance was sigma E square. So if you had your V does not turn out to be zero mean, the model is no good. Okay. So I've already talked to you about equation error model in some in very briefly, just to show you the difference between output error and equation error models. But it turns out that if you were to look at an equation error model, its autocorrelation. So an equation error model, as I told you, was AY minus BU. And how are you going to model this? If you're going to model this as E, it's the so-called ARX model. If you say, no, E is known as white noise. Okay, E is white noise. White noise, because its autocorrelation looks like this. I told you, it's completely uncorrelated. So its autocorrelation looks like this. That is at expected value of, so what is RE of tau? It is expected value of t into E of t plus tau. Okay, when tau is equal to 0, RE of tau is the expected value of E square t. And this expected value I know is sigma. So this value over here, which you're seeing, is probably sigma E square. But because it was completely uncorrelated, so I kept on telling you, see, when I'm here, I don't know where E of t plus 1 is going to go. If this is E of t plus 1 would be here, it would be anywhere. So we say that E of t plus 1, this is t plus 1, is not correlated with E of t. Knowing E of t, I have no clue what E of t plus 1 is. So when tau is equal to 1, Re of 1 is equal to 0, theoretically. Okay. And that you see when you take samples, you can see with this 95% confidence bound that they're very small. That is white noise. Its autocorrelation is essentially the direct delta function. Okay. Now, so when you use equation error models and you get your you get this as your estimate of E. So you can, there's too much information I'm giving you. Okay. So you will say, but I don't know E. So yeah, we don't know E, but I can always find out an estimate of E. And how is that? Because once I have got this A and B, then I can just run this with my estimated A and B, and I will get an estimate of E. And then I can find out the autocorrelation of that. Okay. When I do that, I get a sample autocorrelation, not the population autocorrelation. And those sample autocorrelations tend to be small numbers. Okay, so if you are still wondering, why this is called white noise, then without getting into details, if you were to plot the power spectrum of the signal, okay, so in for example in Octave you can use the command xcore to find out the autocorrelation, okay, or the cross correlation. Then you can also find out the power spectrum in MATLAB, and maybe I will show it to you in the next class. So you will see that the power spectrum of white noise, at all frequencies. So this is frequencies, and this is the power spectrum of E. You will see theoretically it's just a straight line, and the power spectrum is essentially the Fourier transform of your autocorrelation function in the frequency domain. So when you look at white noise or at white light, we know that white light has equal power of, contributed in it of lights of all frequencies. And that is what you see over here, that white noise has all signals at all frequencies have equal power, as you can see by the straight line. And that is why we call it white noise in analogy with white light. Okay, so I've given you, I think I've given like not a very well laid out uh, development, but I hope you get some idea as to where these time series models are coming from. Okay, uh, so as I said that you have this ARX model, and let's look at an ARX model. Okay, so it'll be y of k is equal to, so because of that polynomial, I will write it like this: y of k plus a1 times y of k minus 1 plus a2 times y of k minus 2 is equal to b1 u of k minus 2 plus b2 u of k minus 3. So note that there are two, there is only one input plus ek. Okay. And now I know that if I use my shift operator, I can write this as y of k into 1 plus a1 q inverse plus a2 q to the power of minus 2 is equal to b1 q inverse into u of k plus e of k. Okay. So what did I told you, it is really this ay minus bu. How do I model it? And now you can see that this is nothing but ay. And so I will write this as ay minus bu is nothing but e of k. I decided to model this residual by white noise. That is an ARX model. So an ARX stands for auto-regressive with exogenous inputs. And it is very, these terms have come from econometrics and not from, control or signal processing literature. So they think of y as auto-regressive. The value of y regresses on its own previous values, auto-regressive, and there are and there is an external input u. Okay, so it is auto-regressive with external input is ARS. Okay, again, so there are many aspects, and maybe I can continue at my 7 o'clock lecture where I will show you how to use the SysID toolbox in MATLAB. This toolbox was, actually originally written by Leung, by that author whose quote I had shown you, who has a very famous book called System Identification Theory for the User. And it's a, so if you have MATLAB, you can bring it along for the next session. So let me stop sharing, and maybe if you have a few questions we could possibly discuss. So in over here we have a course which is a semester long course on system identification. So a lot of these things are slowly developed with a lot of backgrounds and basics and all that. And this is just to give you an idea. I will share with you some what kind of projects that can be done as part of time series analysis on Moodle. So let me. Is there any question that I could respond to?
So I have a question. If others, we can give first chance to participants. Otherwise, I can ask one question.
So we all are participants. Abhilasha, please go ahead.
Okay. So, sir, I was just thinking this autocorrelation analysis, can it be used for this, how linear or non-linear analysis? I mean, can we use this as a for understanding whether the correlation is linear or non-linear between those two random processes, or we can say random variables? So.
Yeah. So in case of autocorrelations, when you use them, you really are using an expectation operator, which is a linear operator. Now, to understand if there is a non-linear evolution, that is x of k is not a function of x of k minus 1, but I mean not a linear function of x of k minus 1, but it is a non-linear function of x of k minus 1.
Yeah.
For example, let me just go back uh, over here, and so I can, for example, write over here. So you see, if you have x of k is some non-linear function x of k minus 1, and now you were to do the expected value of x of k into x of k minus 1, then you will realize that because of this non-linearity, uh, g of x of k minus 1 into x of uh, k minus 1, okay, it's not so straightforward to use it. Okay, so this is where it has evolved over finding out. So the first thing is, of course, to use something like a time series model like we discussed in class. And what you will see that if it is non-linear and you are using an equation error model, you will find that these autocorrelations are, can be very erratic. So you will not have this kind of impulse. Even as you try to increase the order, you try to increase NA and NB, you will find that you cannot see some relationship, provided you have enough data. That is often an indication that you can go to using nonlinear constructs like Wiener models, or if you want to go to recurrent neural nets or LSTM models. So the autocorrelation is by design to look at these simple relationships. If xk minus 1 is a times xk, or I'm sorry, if xk is a times xk minus 1, this would have turned out to be very nicely x square k minus 1, okay, which would be some covariance or connected to the variance. But here you could not have brought that a out, or there is nothing to bring it out. And so it depends on this non-linearity, and so that manifests itself as, the non-linearity is playing a role. And so you don't see this kind of a behavior, a stable behavior, and that is often an indication that that this is not.
Non-linear correlations might exist there. Oh,
Yeah.
thank you, sir. Yeah, that's
Okay. Yes, surely we will share this video, and um, so if there are no other questions, let's meet at 7. Okay. So I will keep my session on, and we'll just reconnect at 7. Thank you, everyone.